So we're going to take a look at the next two tests today. One is alternating series test, and the other one is the ratio test. By the way, this is also coming from your handout, so if you have that, you don't have to bother maybe writing it. But if you want to write it, of course you can. This is a series that applies, as the name suggests, to only alternating series, things that are oscillating in sign, plus, minus, plus, minus. So the series test that we've learned so far, we're applying to positive series. So this is the first one that applies to an alternating series. And this one, I think, is a really, really easy test. All it says is, check to make sure that a sub n goes to 0. Check to make sure that the limit of a sub n goes to 0. Again, the bottom of your handout is where this test is listed. The second condition is almost redundant. Because if you think about it, it says that a sub n plus 1 should be less than a sub n. That means that the series, the sequence should be decreasing. This means, the second condition means that the terms of the sequence is decreasing. But 99.9% of the time, if a sequence is going towards 0, the terms are decreasing anyway. So usually I almost ignore the second condition. I usually assume if the limit is going to 0, it's decreasing anyway. And like I said, all the examples I have seen in this section, if the limit is 0, they also are decreasing. There's only one example the book has. If you look at that section, the solved examples, they have only one example where there's a contradiction there. So to save you a lot of time, I think we're going to ignore the second condition. As long as you can show the limit is 0, we're going to assume the series is actually convergent. So let's take a look at the first one, the first example. Summation of -1 to the n times 1 over n. First of all, is that an alternating series? How do we know it? The trademark is -1 to the n, right? That tells us it's going to be alternating. What if it had been -1 to the n plus 1? Would that be alternating also? -1 to the n plus 1. That's alternating also. What if it had been -1 to the 2n? -1 to the 2n? Would that be alternating also? Now 2n is an even number, right? -1 to an even number, is that alternating?
-1 to an even number power alternate.
-1 to an even power?
Well, like -1 squared is positive 1.
This one is not alternating, right? This is always going to be positive 1, right? But if the power is n or n plus 1, it's going to be alternating in sign. Okay, so the first example here is clearly going to be alternating series. All you have to look at is the limit of 1 over n. What is the limit of 1 over n as n goes to infinity? 0. So, and 1 over n is decreasing. We know that anyway, right? So therefore, the given series converge or diverge? Converge by the alternating series test. Now, what if there was no -1 to the n in front of it? What if it was just summation 1 over n? Would that be convergent also? What if you had this? What do we know about this series? This is also known as the harmonic series. What do we know about that? That is a p series, right, with p is equal to what? P is 1. So is it convergent or divergent? Divergent. So there's a big difference between this one and the alternating, because why? Think of this one as 1 plus a half plus a third plus a fourth. You keep adding more terms, right? The other one is going to be -1 plus a half, -third plus 1/4. So it's not growing as fast because you're adding something, you're taking away something. You're adding something, you're taking away something. So that one converges easier than this one. And as we've seen, -1 to the n times 1 over n actually converges. Okay, how about the next example? -1 to the n plus 1 times ln n over n. So this is example 1. Now we're doing example 2. Take a limit of the portion that is not alternating. Take a limit of a sub n, ln n over n. What do we know about this limit? Okay, Gracie suggested it's 0. Would you all agree with that? This is one of our special limits, right? You could always apply L'Hopital's rule if there need be. But we know ln n is one of the slowest growing functions out there, right? Divide by n, the ratio goes to 0 indeed. So what can we say? The given series converge by alternating series test. If you wanted to, you could also confirm on the graphing calculator that this is indeed a decreasing series. That if you graph it and it goes down, as x goes to infinity, it's a decreasing function, ln x over x. You could check the second condition, but like I said, I'm not going to be picky about that. Just show me the first condition. I'm fine with that. Okay, how about number 3? Is this one going to be convergent or divergent? What do we know about this one? Can I even apply the alternating series test on this one? Because this one can be written as, what is -1 to an odd power? Because 2n plus 1 is always going to be odd, right? So -1 to the odd power is always going to be, think of like -1 to the third. What is that equal to? -1. -1 to the fifth. Also -1. Any odd power, you're going to end up with -1. So that's really like a fake power that it's just, we might as well just write this. So this is not alternating. This one is basically pull the -1 out. You're summing an infinite sum, and then you're multiplying it by -1, or you're basically adding up all negative terms. Another way to look at it. Is this one convergent or divergent? What can we say? If you take the -1 out, what do we know about this one? What do we know about this series? The positive one, this one. P series with p equals 1, that one diverges, right? So that means this given series diverges as well. We couldn't even use the alternating series test on that one. So the given series diverges. P series times the -1 is still infinity. The given series diverges. P equals 1. And it's not alternating. Okay, how about the next one? Take a limit of the inner portion. Is this one alternating? -1 to the n plus 1? It is alternating, right? Either -1 to the n or -1 to the n plus 1. It's going to give you plus, minus, so alternating in sign. So let's take a limit of the a sub n portion. What do we know about this limit? This is a good review of limits in a sense, right? What is this limit? Good suggestion, infinity degree, not the degree, but the higher term is n factorial. We've learned that famous inequality that I gave you on the first section. N factorial grows much faster than exponential, and the ratio goes to 0. So since that limit is 0, and since this is alternating, the given series is what? So what can we say? Does it converge or diverge? If the limit is 0 of the inner portion, look back to our theorem. If the limit is 0, then the series converges. So in this case, the given series converges by alternating series test. Okay. And the last one. What do we know about this limit? So what do we know about that limit? Right, we can definitely use the alternating series test because it's alternating -1 to the n plus 1. And we're taking a limit of the inner portion as this test suggests. And what is the limit of the inner portion?
2, not 2.
It is 2, which is different than 0. Therefore, right, the series diverge. You could say it diverges either by the n-term test or by alternating series test. It diverges. Yes, Gracie? I'm sorry, did I write 0 there? I said it goes to infinity, but I wrote 0. I'm sorry about that. Right, because the top grows faster than the bottom. What was I thinking? Right, so it goes to infinity, and the series, therefore, diverges also. Sorry about that. Yeah. Right, because we talked about the fact that n factorial grows faster than 2 to the n, that it goes to infinity, but I don't know why I ended up writing 0. So thank you, Gracie, for that correction. Okay, so now let's take a look at another test. I'm going to come back to these later. Okay, another test is the ratio test. Also from your handout, you have a handout that summarizes all the different tests, right? This is on the second page of that handout. Okay. This test works especially well when you have exponential functions. Like, look at the first example here. Exponential functions like 3 to the n or 4 to the n. Also, it works especially well when you have factorials, such as n factorial or 2n factorial, or anytime you have a factorial or exponentials, think of the ratio test. Now, the ratio test is really easy to understand if you think about the geometric series test. Because with the geometric series, what do we have? We had like a plus, where's my pen tool? Okay, a plus ar plus ar squared. So if you took the ratio of any given term to the previous one, what would that ratio be? Like if you took the ratio of a sub n plus 1 to a sub n for a geometric series, what would that be? Your common ratio r, right, for the geometric. So this one is saying, take the ratio of a sub n plus 1 to a sub n. And in geometric, that ratio is fixed. It's a fixed number r. But this is saying it doesn't have to be fixed as long as the limit of that ratio is something less than 1. And remember, for geometric, we needed that r less than 1. So even if it may not be a fixed number, as long as the limit of that ratio is less than 1, it says the series converges. If it is greater than 1, then the series diverges. If it's exactly equal to 1, the test fails, and you need to go back and look for another test. Okay? So now let's do an example to see how this test can be used. Here's our first example. I'm going to go ahead and get rid of the other ones for now. Let's see, move those down. Okay. So let's do this one. Does this series converge or diverge? That is the question. I would say always quickly glance at it from the perspective of the nth term test. If you can prove something with that, it's going to save you a lot of time. In this case, on the top you have basically something like 12 to the power of n. On the bottom, n factorial. Does that limit go to anything different than 0? No, because exponential function on the top, factorial on the bottom, that ratio really goes to 0. So the n-term test goes out of the window. It cannot help us. Now, we just learned that when you have exponentials, when you have factorials, this new test, ratio test, is a good one to apply. So let's apply it. It goes like this. You need to take the limit as n goes to infinity of n sub n plus 1, a sub n plus 1 over a sub n. So assume the given series is your a sub n. So what would be our a sub n plus 1 here? We're going to replace every n with n plus 1. That's our a sub n plus 1. So you're going to have 4 to the n plus 1 times 3 to the n plus 1 divided by n plus 1 factorial. So far I have the a sub n plus 1 portion. Okay. Now I want to divide this by a sub n, but dividing by a sub n means multiplying it by its reciprocal, right? So So what would I need to multiply this with? Multiply this with 1 over a sub n, which is, flip it over and multiply. At this point, you're always going to see some simplifications. Take advantage of those. For example, 4 to the n plus 1 with 4 to the n. What would I be left with? Four to the n plus 1 is 4 to the n times 4 to the 1, right? You can, and you have a 4 to the n on the bottom. So what are we left with? 4 on the top. How about the 3 to the n plus 1 with the 3 to the n on the bottom? We're left with a 3 on the top, right? Okay, how about the n factorial on the top and the n plus 1 factorial on the bottom? I would say always start expanding the bigger factorial. Like in this case, n plus 1 is bigger than n. Start expanding it out. What is n plus 1 factorial? It is n plus 1 times n minus 1 and below. I could really write that as n plus 1 times n factorial. I might as well rewrite n factorial also. That is the same as n times n minus 1 and below. Do you see a cancellation there? Or a lot of cancellations? Okay, so everything after n and below will cancel from the top and the bottom, right? So we are left with what? 12 over n plus 1. And what is the limit of this quantity as n goes to infinity? It goes to 0. The bottom is getting larger. The top is constant. It goes to 0. So that tells us what? It's according to the ratio test, as long as this ratio is less than 1. Again, when you apply geometric, rather the ratio test, think geometric. As long as that ratio, which kind of pretends like to be like R, as long as it's less than 1, it converges. In this case, that ratio is 0. So by the ratio test, the series converges. This is less than 1. Therefore, by ratio test, the given series converges. Okay. Can you try this next one? I'm going to clean it up a little bit for you. And I will pause the video for a few moments for you to think about it. Don't worry about this last one. I don't think I'll be able to do that one today. Just this middle one, number 2. N squared over e to the n. Does this series converge or diverge? I would say, again, first start with the nth term test. Always a good idea. Okay, so we're going to use the ratio test. So we're taking a limit as n goes to infinity of a sub n plus 1. So replace every n with n plus 1, right? Divided by a sub n, or times 1 over a sub n. Okay, let's try to simplify it a little bit. Okay, the top I'm going to leave it the n plus 1 squared at the moment exactly as it is. How about e to the n over e to the n plus 1? There's an e on the top or on the bottom left over. The e to the n on the top with the e to the n plus 1, because remember, e to the n plus 1 is the same as e to the n times e. Now the e to the n's cancel, so you have an extra e on the bottom, right? Would everybody agree with that simplification? Okay, now I didn't expand the n plus 1 squared because all I need to know is that there's an n squared term on the top and an n squared term on the bottom. My degrees are the same. So as you're taking a limit, what would the ratio of, what would the limit be? It would be the ratio of the leading coefficients, right? On the top you have an n squared, on the bottom e times n squared. So what will the answer be? 1 over e. 1 over e. And is that less than 1? Definitely, because E is 2.718, right? So this is less than 1. Therefore, the given series converges or adds up to a finite answer. That's what converges means. The given series converges by the ratio test. Okay, the last one, I'll come back to it later. And finally, there's one more thing I'd like to go over with you, which is related to alternating series. So I'm going to go back to alternating series one more time. And here it is. It's called alternating series estimation theorem. And this is also in your handout. Look at the bottom of the second page. Remember how we did the integral estimation theorem? But that only applies to positive series. If your series are alternating, you cannot use that integral estimation anymore. There is something else you can use, and that is listed on the top of this page and on the bottom of your handout on the second page. It's listed as number 2. If you want to just circle that so you don't have to bother writing it. Joshua, turn the page over. Okay, okay, number 2. Everybody sees where it is? Okay, good. Okay, here is what it is saying. It's very similar in some ways to that integral estimation, because what you're trying to do is you're trying to have an idea about the difference between adding up infinitely many terms and adding up only k terms. Okay? Clearly, if you only add up the first k terms, let's say k is 10, okay? If you add up the first 10 terms, obviously there's going to be an error, right? Because you're not adding infinitely many terms that you're supposed to, but instead you're adding 10 terms. So you expect to have an error. But what is the size of the error? That is the question. And this theorem is very interesting. Here's what it says. The error, or the difference between the infinite sum and the finite sum of adding k terms, that is called the error. It is going to be less than the next unused term. Or really, it's just a positive. You disregard the negative 1 to the n portion. You just look at the other part, the a sub n portion. So it's saying that the difference between adding up infinitely many terms and adding up the finitely many terms is going to be less than the next unused terms. For example, if you add up to the first 10 terms, this is saying the error will be less than which term then? The 11th term. Okay, just look at the absolute value of the 11th term. The error will be less than that. Now, it sounds almost like magic. You know, how could this be? So I want to show you perhaps an explanation of this. Let's see if I can find it. Okay, this graph is going to try to help us understand how that theorem works. I want to show you a little bit at a time. Okay. You know, in a positive series, you keep adding terms like 1 plus a half plus a third. Okay, that doesn't surprise us. They're going towards infinity. But with an alternating series, you have a negative term, then you have a positive term, and a negative. So it's almost like taking 2 steps forward, and then maybe 3 steps backward, and then 4 steps forward. And so you're going a little bit forward, a little bit backward. It's not increasing that much. There's a bound. So think of it as A1 minus A2 plus A3, etc. Okay? Now, first add an A1. If you add an A1, so let's say this is the point 0. If you add an A1 to it, it's going to bring you over here. That's the first sum. S sub 1, you just added the first term. That's A sub 1. Okay, so it's going to put you here. S sub 2 is, which is adding the first 2 terms, A1 minus A2. That means go back A2 units. From here, go back this way to A2 units. Now, that's going to bring you over here to S sub 2, because if you go that many, A1 is from here to here, and A2 is going backwards, negative from here to here. If you subtract, the sum of those 2 terms will be here. Again, you go forward and backward. Now, go forward with an amount of A sub 3. So as you see the blue line, go forward A sub 3. This is where it's going to bring you to S sub 3. Go backwards with an amount. Now, if you were to do this over and over, and remember, the terms are going towards 0 because the limit of A sub I goes to 0. So each time you go back and forth, you're going a smaller distance. So if you go a smaller distance each time, it's going to look something like this. So you go that way, then you go back that way. So it might be something like the limit will be somewhere here. This is the sum of all the infinitely many terms. And what this estimation is telling you is the following. If you were to add up the first 4 terms, A1 minus A2 plus A3 minus A4, if you were to add that one, and if this is the correct answer right here, if this is the correct answer, the sum of infinitely many terms, it's saying that the difference between where you were at after you added the 4 terms, you were here, and the infinite sum. It's saying that that difference, adding the 4 terms and the infinite sum, that difference will be less than the next unused term. And the next unused term may be from here to here, for instance. So it's saying that this distance will be less than this distance. And that's basically all it's saying. Because every time you go, because the limit is going to 0, you're going a smaller distance. You go this way, that much. On the way back, you're going to come a little bit less, a little bit less. So this is your infinite sum S. And this graph hopefully gives you some understanding about why the alternating estimations theorem actually works. Okay, let's do an example with it. Here's an alternating series. It says sum the first 4 terms and comment on the size of the error. Sum the first 4 terms and then comment on the size of the error. Okay. Summing the first 4 terms will be very simple. Just go from 1 to 4. We call it S sub 4, the sum of the first 4 terms. I'm sorry, do you guys need the theorem as well? Remember, the theorem is in your notes, in that handout that you have. You can copy it from the bottom of your second page. Okay, so add up the first 4 terms. Before you can add them, you got to be able to list them, right? So let's list them. The first one will be negative 1 over 1 to the third. Is the second one going to be positive or negative when n is equal to 2? So what do you get when n is equal to 2? I have what you get when n is 1. If n is 2, what do we get? Positive 1 over 2 to the third, right? Plus. And the next one, when n is 3? One over 3 to the third. Next one. Four to the third. Okay, let's go ahead and add these terms and see what we're getting. It says estimate the infinite sum using the first 4 terms. Okay, did anybody get negative 0.896?
Yeah.
Okay. Now, we didn't add up infinitely many terms. We only added up the first 4 terms. So clearly there's going to be an error, right? And the theorem says to find the size of the error, all you have to do is take the next unused term. The next unused term would be, if you add it up to the first 4 terms, your k is 4. So take the 5th term, so which will be 1 over 5 to the third. So what is 1 over 5 to the third as a decimal? You only look at the positive, the absolute value, basically. You disregard the negative 1 to the n portion, and it's 0.008. Not bad, huh? We didn't add up infinitely many terms. We only added the first 4 terms, and yet we know if we were to add all these infinitely many terms, you know, we wouldn't be that far off from this estimate we have. Would be perhaps as far as just 18 thousandths far from it. And one way to write this is if you call this actual sum capital S. Basically, we're saying that capital S is going to be between our estimate minus the error and our estimate plus the error. So we feel like we've pretty much narrowed down what that infinite sum will be by finding the first 4 terms and then the error. So whatever that infinite sum is, it should be something very close to, roughly speaking, 0.90 something, like negative 0.90. Okay, one more related question. Any questions about this one? Anybody who hasn't copied it yet, or any questions? So when are you going to use this estimation theorem versus the other one? This one only works for alternating series. The other one, the one with integral, that one only works for positive series. Okay, so depending on which one you have, you should use the appropriate estimation theorem. Okay, let's do this one. Same question, but asked a little bit differently. They're not telling you how many terms to add this time. You're going to determine that. They're asking you how many terms should we add so that we are away from this infinite sum by less than 0.001. By the way, today I'm not going to have a chance to talk about absolute convergence and conditional. On your group activity, just ignore those. Just answer this question. Does a given series converge or diverge? Don't worry about the terms absolute or conditional. Just does it converge or does it diverge, like we're doing here, okay? Okay, so this is an alternating series, correct? So we can use the alternating series estimation theorem, right? So if we're going to use the first k terms, if we're going to add up the sum of the first k terms, then the error should be less than what? The next unused term, disregarding the negative 1 to the n portion. Okay, if you use the first k terms, what will be the next unused term? K plus 1, what? K plus 1. Because if you were to write it out, say you have negative 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial. Exactly. This should be 1 over k plus 1 factorial, right? Like if you add up the first 3 terms, the error should be less than 1 over 4 factorial. If you add up the first 10 terms, the error should be less than 1 over 11 factorial. If you add up the first k terms, the error naturally should be less than 1 over k plus 1 factorial. And we are given that, we need to know what should the error be so that this error is actually less than 1 over 1,000. That's what we want. So we need to solve an inequality here once again. Yes. Yes, because the theorem says, let's go back to the theorem. It says right here, you should use a sub k plus 1 as your error estimate. If you use the first k terms, use the k plus first one for the error estimate. Always the next unused term. Like if you use the first 10 terms, you will use the 11th one as your error estimate. And remember, this only works for alternating series, okay? All right, so we're going to solve this inequality. Do a cross multiply once again. 1,000 less than k plus 1 factorial. Okay. Because go back to the definition. Go back to that. You see, a sub n is only this part. A sub n is just this part. It's a very good question you're asking because you're paying attention to the wording of the the theorem. Very, very good that you're being careful. But in this case, no need to worry because a sub n, in this case, is defined to be everything but the negative 1 to the n portion. So when we talk about a sub k plus 1, again, you don't worry about the negative portion, just everything else. Okay, so we're solving this for k. Hopefully, we're going to solve it for k. I did a cross multiply. The question is now, how do you solve this equation? Because if you have a square on one side, you would take a square root to get rid of the square. If you have exponential, you apply ln. With factorial, we really don't have a way to solve it, so we're going to trial or error. Okay, so let's write down the first two factorials that we know of. So for example, 4 factorial is 24. And by the way, you guys have a factorial key under math probability menu. In case you want to use that, you would put your number on the home screen. Then to get a factorial command, go to math probability and pick the factorial. From there, you can evaluate these quickly. And you can also do second enter. That way, just change the number, keep the factorial on the home screen. 5 factorial, I believe, is 120. 6 factorial is 720. 7 factorial is basically 7 times the previous answer, which is 5,040. So the first value that was greater than 1,000 was 7 factorial, right? So this should be 7, because if the right-hand side was 6 factorial, it would not be greater than 720, right? So the right-hand side, the k plus 1 must be 7. That's the first one. K plus 1 must be 7, because 7 factorial is greater than 1,000. So what is k then? Okay. So if k is 6, let's double check. If k is 6, you would put it into that inequality. 6 plus 1 is 7. 7 factorial is 5,040. And that is greater than 1,000, it works. If you put anything less than that, if you put like 5 or anything less, it's not going to work. So that means we must add the first 6 terms. Add the first 6 terms to estimate this infinite series with an error less than 0.001. Why did I use? Oh, I just want to give you a list of factorials to show you what they were, and from there we picked the correct one, because we wanted to find the first one that was going to be greater than 1,000. Okay? How do you set this one up? Same question. If you like, take this one home, since I seem to be running out of time. Same question, but just write this one. Divide by n to the 4. The question is, how many terms should you add so that the error is less than 0.005? So how many terms should you add so the error is less than 0.005? Okay, we might as well finish this question also for the record. So let's go ahead and answer the question. The question was, how many terms should we add for the given series? How many terms should be added for the given series so that the error in estimating the infinite sum is less than 0.005. Okay, and the given series is summation n from 1 to infinity of -1 to the n plus 1 divided by n to the 4th. Again, clearly this is an alternating series, so we can use the alternating series estimation theorem. Oops, what is going on there? Let me fix. Okay, so let's say that we're going to add up the first k terms. So let's say that we're going to add up this series from 1 to k, -1 to the n plus 1 over n to the 4. And by the alternating series estimation theorem, we know the error would be less than the next unused term disregarding the negative 1 to the n plus 1 portion, so that will be 1 over m plus 1 to the 4th power. Now we want that to be less than 0.005, which is 5 over 1,000. And I better use k, not n, since I assumed I was adding up to the k terms. So the next unused term would be 1 over k plus 1 to the 4th power. Okay, to solve this inequality, I will cross multiply. So 1,000 is less than 5 times k plus 1 to the 4th. Divide by 5 both sides. So 200 is less than k plus 1 to the 4th. Take the 4th root of both sides. So k plus 1 is greater than the 4th root of 200, which happens to be 3.76, I believe. So we want k plus 1 to be greater than that. So k should be greater than 2.76. So when we subtract 1 from both sides, and the first integer to satisfy that is 3. So if k is 3, it will be greater than 2.76, and it will satisfy the condition set by the problem. So that means add the first 3 terms. And we're guaranteed that that sum will estimate the infinite series with an error less than 0.005. And just to check this answer really quickly, if we add up the first 3 terms, okay, then the error term would be 1 over, since we add the first 3 terms, the error term will be less than 1 over 4 to the 4. The next unused term is the 4th term. And 1 over 4 to the 4 is 0.0039, so roughly 0.004. And clearly that is less than the error that we were looking for, which is less than 0.005. So it looks like adding just the first 3 terms is going to be sufficient in estimating this infinite series with a reasonable accuracy.